Hello and welcome to session 347 in the AISafety.com reading group. Tonight we'll be discussing the article Safety from Honesty in a Disinterested AI Predictor by Joshua Bengio and others. So before we talk about the article, I want to be upfront that this presentation is only about section 1 and 2 of the paper, and I've only skimmed the rest, which means that there are likely mistakes, and those are all the mistakes are my own, of course. So the paper's title include an honest, disinterested predictor. And I want to draw attention to that because as I read the paper, honesty isn't central to the work at all, at least as far as I can tell. The predictor is merely predicting as well as it can. A way I would have perhaps changed this title would be a never agentic oracle to distinguish it from standard oracles in the AI safety literature, which are superintelligences that may or may not be agentic, but are then placed in a box and prevented from being agentic. And the idea here is that there is never any agenticness. But let's go back to the paper. That was just my thoughts on the title. So Bengio introduces the problem of misalignment and discusses all of this in a framing around learned implicit agency. Learned implicit agency is a big part of instrumental convergence, where agency helps the AI in not being shut down and all these other convergent instrumental desires. And sure, learned implicit agency is central, but it doesn't really have to be implicit, because in practice, a lot of agency in Claude and ChatGPT aren't something emergent that implicitly happens, but an explicit target of the training. Learned implicit agency is defined or explained as goal-directed behavior that wasn't explicitly specified by the designer. And how does that enter into these models? Joshua Bengio speculates two places. First, it comes from the pre-training that imitates human agency, like humans desire power, and if it imitates that, then it may be agentic in the same way we are. And the other is in reinforcement learning, in particular reinforcement learning from human feedback, because the output of this training and the output of the actions are then rewarded according to their downstream effects, whether the reviewers click the thumbs up button. And so this paper is about designing an AI that does not at any point whatsoever contain any of these sources of agency. So once all this training process without reinforcement learning or imitation learning, it results in what the authors call a disinterested predictor. And based on around this disinterested predictor, they propose a scientist AI. And the idea, the conceptual distinction that underlies this scientist AI is that it's possible to distinguish two things. Honestly, predicting what agents will do and what consequences of their actions will be, like a forecaster that's predicting the weather, and on the other hand, like being an agent that makes predictions that influences the outcomes. So that results in this overall process for training and deploying a scientist AI, which we'll go through later. The first step is to do a lot of things with data. They need to be contextualized in a rather involved process, and that's really a central part of the work. And then you need to train a predictor, and it's trained in two different ways called System 1 and 2. Here you can see them as sequential steps, but they're actually meant to happen concurrently. And then finally, once we have trained this predictor, it needs to be deployed. And it's deployed through a scaffolding that doesn't have any AI, that's just directly coded. And guardrails, where the central guardrail is the model itself. So that was the overview. Let's dive into first how Joshua Bengio proposed that we create a data set that does not have any human imitation. So first we have some of the input, which is just simple facts. This could be like scientific facts, this could be mathematics, logic, some code that is provided together with the results of running this code. So these are basically uncontroversial ground truths, which are obviously important for a scientist AI. But that is only a very, very small part of the actual data, because we have a lot of data, like the entire internet, and this is not directly fed into this AI. What we do instead is that we make statements from these together with very explicit meta information about who said this and when did they say this. So this means that we don't have in training data a lot of true or false things. Like we don't have a claim that the Earth is flat. We instead have the claim that the Flat Earth Society have said that the Earth is flat. And that means that all the data is true. And that's important for the data training, because when we want to approximate a Bayesian posterior, then we need to condition on all the true things. There is, as I see, some very significant problems with this. For instance, compared to reality, the dataset will necessarily be exceptionally sparse. Like there are a limited number of tokens, but the number of possible statements is just very, very large. And when you have such a large dataset, like data space, and you need some statements, then these statements will be sampled in some way. And the way you sample from a very large dataset is something that can have a dramatic effect on the eventual properties of the system. So doing this in a consistent, principled way seems really, really difficult. And the problem is that you cannot do this for a part of the training and then do some more depending on the results. The entire point of this training is that you don't feed back the resulting predictor into itself. So you have to do it like in one step, or otherwise you need to throw everything out. And that seems like a really difficult thing to do. And there's a lot of potential vulnerabilities and pitfalls I can see in this. Joshua Bengio in this paper does not make any attempt at answering whether this is possible. They are writing that this is a requirement for the data collection and contextualization, and they're not really specifying an algorithm. But I don't think this really is sufficient for us to think about this. Like, we can't evaluate whether this approach is feasible by just saying these are the requirements. Like, we are talking about a fundamental semantic transformation of every single data point, and this can go wrong, and there's an inescapable weakness if there is either biases or worse, adversarial selection. Like if an untrusted agent are able to decide what statements are true, that is a certain weakness. So one thing the authors make sure to write is that this model is not initialized with a large language model. And I guess that's good, but like we have a lot of data, we have the entire internet. How are we supposed to annotate the entire internet without using untrusted frontier models? That seems really, really difficult. Okay, so the first part of the training is where we have all these input statements, and each are given a variable, like how much do, and we need to train on this to approximate a Bayesian posterior with stochastic gradient descent or something like that. But we also add a set of latent variables to each statement. So that means that we're not just saying the flat Earth society is saying that the Earth is flat, but we are explicitly adding to this model some underlying variables like, is the world flat? So these latent variables ensure that we're not just training a gossip model that only knows about who said what, but we also have a model of the world. And of course, presumably the hope is that if a lot of people are saying that the Earth is round, then the model will be more likely to learn the underlying statement, like provided, of course, it's consistent with what it otherwise knows that the Earth is round, rather than having to learn about all the people who said this. Then it's much simpler, and hopefully the model will end up learning that. But it's, of course, an empirical question. The important thing about this training is that it's not embedded in any kind of reinforcement learning. So it has to be disinterested in the world. That ensures that we don't select predictors in a way that is casually connected to the outcome of the selection. And the authors really clearly mean to distinguish this from reinforcement learning, from human feedback. Because that selects from models that take actions that are approved by raters and these kind of downstream effects. That's the central part of their argument. But my understanding is that most of the optimization pressure on modern models actually comes from reinforcement learning with verifiable rewards. And these verifiable rewards don't actually directly connect to eventual deployment outcomes. And I would like the authors to write something about this, if it is in fact the core way that we train models right now. Okay, so once you've trained this predictor on all these variables, then you can then query the model, do inference, and you can just ask, give it some variable and say, what is the prediction of this particular statement through a feed-forward pass through a neural network. They analogize this to Kahneman's System 1 thinking. I haven't actually read it, and I thought it wasn't even an analogy, but just the thing that System 1 was. So it's described as fast and intuitive, but not always coherent and brittle outside of distribution. These are, of course, important drawbacks. I see this kind of feed-forward System 1 as a kind of distillation of the other kind of prediction that the predictor also does. And that will be the System 2 part, which is another part of the scientist AI that is called, the predictor does System 1 and System 2 prediction, but the System 2 prediction is helped by another component that the paper calls the explainer. And the explainer is a learned proposal model that suggests some statements that are likely relevant to the current query and the current context. When I read about this explainer, I thought this is basically a large language model, right? Because it produces relevant text for this context. Relevant means like what is low loss. If you consider the explainer as an LLM, then this subsystem, of course, becomes really, really important to the scientist AI, because it's not enough that the predictor is disinterested. If the explainer is an LLM that has a lot of different potential unsafe properties, as far as I can see, at least in the first 2 chapters, there isn't really made any attempt at looking into the safety of the explainer model. And that seems like an important vector for agency or other misalignment to happen. Okay, so the explainer proposes some statements that are relevant, and then the predictor can do can see these potentially related statements and assign probabilities to those, kind of like in doing a kind of chain of thought reasoning. And of course, at the same time, it's evaluating the system one statements and it's aggregating the results. They write about Monte Carlo and weighted averages, which is probably empirical questions, what works best. But I'm really worried about the explainer, right? Because if you imagine that the explainer is a super intelligent, misaligned AI, I would be very worried about having it be able to propose statements in a specific biased way that might potentially strongly influence the predictor. One of the problems, of course, is that the explainer might have full knowledge of the predictor. The paper doesn't seem to assume that it doesn't have that. And given that, it seems very likely that it could produce some really biased inducing potential explanations. The authors are more focused on the problems that arise when this model is deployed. But I think if the training process is being biased and manipulated by this explainer model, I could definitely see a smart misaligned explainer being able to introduce blind spots during training. Okay, let's turn to the last part of the process for the scientist AI, which is the monitoring, the guardrails. And here we want to, Joshua Bengio and the authors want to do better than the current untrustworthy monitoring scheme. So if you have a current model, Claude or ChatGPT, then my understanding of the way it works is you have some output from the newest model, and it passes through some kind of monitored channel on the way to the user. And there's a different model, often the last generation of models, which are more presumed safe, that monitors this channel and cuts it off if it believes that it's being used, is doing something bad, basically. And of course, the classic setup often fails. We've seen it fail recently in pretty dramatic ways. And like the most interesting from a theoretic point of view is the fact that the newer model is smarter than the monitor. How do you deal with that problem? But there are many other problems. Like if both the models are misaligned, then they could potentially conspire against us. And if the models share a lot of data or training processes and this kind of thing, then they may have the same alignment failures. And so the proposal in this paper is that it should be the same model, the same predictor model that is used as monitor. So it will evaluate, it will give some kind of predictions, and then the same model will run one more time and say, if this output is revealed, what would be the consequences of this output? And if it's sufficiently bad, then it will blank out the output, basically. And that, of course, solves the entire problem of the monitor being weaker than the monitored system. And I think it also removes basically the risk of the models conspiring. There could still be correlated failures. Correlated failures seem much more likely if it's literally the same model being run twice. One thing that I would highlight is like if the agency removal process isn't perfect in some way, you could imagine that there's a bit of agency, and if this bit of agency is both used for the predictions and for the monitoring, then this kind of guardrail could fail dramatically. Apart from this this guardrail, there is also like some agency is probably necessary if you want to like have it write code and things like that. And so the idea is that all the parts that require agency are scaffolded in a way where there's some direct code written that is human auditable. That's at least the construction. And I just want to flag that writing some auditable code for this kind of agency, that seems like a really, really difficult thing to ensure that there is no loopholes or something like that, because you could imagine that if the predictors turn out to have some agency, and then they are also potentially super intelligent, and that means that having code that is auditable is potentially really, really difficult if your adversary is a super intelligence. Okay, so what is the argument that this entire construction is safe? Let's turn to that. There is also a lot of discussion about to what extent it will be like accurate and whether it will perform. I'll mostly skip those. I want to focus more on the safety arguments and the intuition behind them. So a core underlying assumption is that among all predictors, almost none of them are malign. And I think I can see the argument for this, but I can also see counter-arguments. And the classic counter-argument is the claim that the universal prior is malign. I think it is plausible that the predictor might reason about remote agents and that kind of thing. It's definitely not something that can be ruled out a priori. Another fundamental assumption is that any kind of takeover require a number of sequential coordinated actions that are really far from the training target. And I think this is often a correct assumption. One of the ways where it might fail is if we're talking about gradual loss of control scenarios, because gradual loss of control scenarios may involve a lot of small actions that all are locally correct, locally consistent, where we give up more and more power and act and end up in a place we did not want to. With these assumptions, then the safety can follow from ensuring that the training process does not systematically is more likely to find the unsafe predictors. And of course, standard reinforcement learning does precisely that. Right? If you have an outcome-based setting, then you're much more likely to find convergent instrumental drives and implicit agency. So the safety proposal hinges on this disinterestedness. And I think I agree with this. And I think this is the core central intuition behind this and a lot of other technical safety work. I would have much preferred if there existed a rigorous treatment of this subject rather than, just intuitions. I think someone ought to do that. The safety of the scientist AI relies on quite a few assumptions, and I'd like to go through at least some of them. The first is that the argument is not really about whether the entire scientist AI is proven to be safe. As far as I can see, the proofs refer just to the predictors and not to the entire system. And of course, this is reasonable. You've got to start somewhere, but I think this is a very substantial limitation. It should be in the abstract, basically. And second, there's a definition of safety that incorporates assumptions about bad data and bad prior. So you can say, like, if you have some really bad data or you have a really bad prior, and then you prove based on this that you don't do anything bad, then they call it safe. But I don't really like to use the word safety for something. Like, if you have an AI where turning it on results in everybody being killed, then I don't want to use the word safe for that. I want to reserve the word safe for things that don't kill us. Then there's a question of what constitutes harm and like what are the acceptable thresholds and risks levels. And the paper basically assumes that this can be that these are present, but these are things that I think are really, really non-trivial to formalize. And not only are they very hard to formalize, you also need to do some kind of political prioritization on top of all the conceptual confusion. Again, I don't really demand that the authors formalize the concept of harm here, but I think I would have liked a more explicit admission of this limitation. Finally, they assume that there is only one predictor, and whether it's possible for bad things to happen with multiple predictors, that's something they leave for further work. But intuitively, this seems problematic, because if you have a large number of scientist AIs, then they could each contribute a bit to some kind of joint catastrophe. This seems like very plausible to me. Okay, but given all these assumptions, what are then the actual core of the safety argument? Of course, we won't go through the actual formalization of the proofs. We'll stay at the level of intuitions. So one of the core intuitions rely on a loss band. So if you imagine you're making some kind of equivalence class of all predictions based on how much loss they receive. And then the idea here is that you imagine you have a list of predictors and they have like an error budget in a sense, like the loss corresponds to how many errors they make. And in general, you would expect these errors to be like distributed around the space of predictions in some uniform, random way. And so the idea is that if you want to make a misaligned predictor within some kind of loss band, then it will be misaligned in the sense that it will make bad predictions on important areas, and that means it will use up some of its loss on these bad predictions. Okay, so the underlying assumption is that coordinated actions over time are required for substantial harm to be likely, and these dangerous predictors are rare at every level of loss. And the training process doesn't disproportionately find these dangerous predictors. Based on these three things, then we arrive at this formula, which is the central safety result of the paper. So on the left-hand side, we have the probability of finding a dangerous predictor Q, and this is bounded by a product of two factors. First, at a given level of loss, what's the fraction of predictors that are inherently dangerous, and then multiplied by how much the training process pushes the found predictors towards those that are dangerous. Okay, so that was the central safety result that is proven in the paper, but we haven't gone through the proof. Joshua Bengio considers and answers some possible counterarguments to that case. The first is that you expect convergent instrumental subgoals for all tasks, and making accurate predictions is a task, and you can't fetch the coffee if you're dead, right? So there will be a convergent instrumental subgoal for staying alive until you can do the actual prediction. But they answer that the training is completely invariant to the downstream consequences. So this kind of coherent instrumental drives does not apply. A second objection is Mesa optimizers. Like, might a predictor learn a consequentialist optimizer as part of its reasoning? I must unfortunately admit that I did not quite understand the answers to this objection. Possibly it is that there is, assuming that there's absolutely no agency at all in the system, then the process of how a Mesa optimizer could get going can't get started. It's possible that it's that. If that is true, then the problem here is that it's a very brittle system, in that you're trying to make an oracle that never at any point have any kind of agency at all whatsoever. And the problem is that once you get a tiny bit of agency somewhere in this enormous system, then Mesa optimizers seem to be possible to select for. A third problem is that some of these predictions that it's giving might be censored, and that's a thing that is not really modeling. Like consider a classic example of a self-fulfilling prophecy, whether a bank is solvent. Right? If you make a prediction that say this bank is solvent, then that will have some very strong downstream effects. And if this is censored, it will change, and you're not certain to get some kind of fixed point through that. And they go through some ways to get around this, but ultimately they aren't really that worried about this. You can basically just take any fixed point. The main worry is whether you take a whether there's anything safety relevant in how these self-fulfilling prophecies go, and that's their focus to avoid that. Another potential problem is eliciting latent knowledge, that the model might produce some output, and then this output doesn't in fact reflect what the model actually thinks. Like, is it actually thinking about takeover when it gives some kind of prediction? Well, the construction doesn't require that it say that. So the architecture does map the individual statements to variables, and I think this is in fact one of the greatest point in favor of this architecture, that it is exceptionally interpretable. You have a model where all the variables correspond directly to statements, and that means that even if you cannot elicit the latent knowledge, then you can go into each variables and then actually see the statement that they correspond to. And I think that's a great advantage. Okay, so that concludes my presentation of these two first sections. So here is my own high-level thoughts on this work and where it sits strategically. So I've been quite skeptical in this presentation, both about the safety arguments, and I'm also like, I would be very surprised if this turns out to perform well. But I don't think that the fact that this is somewhat half-baked is even a major problem, because a lot of these problems seem fixable. I think in particular, one way that I can see this work being dramatically easier is by restricting the statements to those that are related to corrigibility and power seeking, this kind of thing. That would dramatically shrink the domain, and that could make it much more tractable. I would also like to see some kind of formalization of the problem with reinforcement learning. I think that's both helpful on a technical level, and it's of course also very helpful for coordination. But I think something like the scientist AI is not at all on track to replace ChatGPT right now. And I think Joshua Benji would mostly agree on this. But I'm not dismissing the research for that reason, because from a strategic point of view, it's a lot easier to argue for a pause on capabilities if there is a plausible, safer alternative being developed. And even if the scientist AI is never actually deployed in reality, then I speculate that this kind of research could still have a substantial strategic impact, because the threat of potential consequences can be really powerful. So here is a totally fictional scenario. It doesn't matter that it's fictional because it's something that can be imagined. So you can imagine after some kind of AI catastrophe, then the Frontier Labs employees may be charged with knowingly deploying AI that is not safe. And presumably the actions that they're taking right now involve a risk that they don't have any kind of official permission to take on behalf of humanity. So post hoc, after the fact, they may need to answer in a court why they chose not to investigate the scientist AI. And they would answer, I would guess, that they did this for reasons of technical necessity, right? The scientist AI had some new known vulnerabilities, and if these vulnerabilities are strictly dominated by those in the systems that are already deployed, then that defense might not fly. So if we go back to reality, then the Frontier lab employees might imagine a scenario like this, and that may cause them to be more cautious, just because this research into safer architecture exists. And that is one of the ways I imagine this could be really helpful. This concludes my presentation on safety from honesty in a disinterested AI predictor by Joshua Benjo et al.